Hello everyone. So this is our last chapter, that is kinetic theory of gases. So what we are going to learn in this chapter, let's start. First of all, Avogadro's law. All gases occupying the same volume under the same conditions of temperature and pressure contain same number of atoms or molecules. This already you have learned in chemistry, same law, that is V by N is always equal to constant. Next, 1 mole of substance contains Na elementary units, and where Na is what? Avogadro's number. If 1 mole of substance is there, how many elementary unit it consists? 6.023 into 10 to the power 23. Now capital M is equal to small m into Na, where capital M is mass of 1 mole of substance and small m is mass. This even already we have learned in thermal properties of matter in ideal gas equation. Yes, no? Okay, so note down this. So let's solve one problem. Calculate the number of atoms in 39.4 gram gold, and molar mass of gold is 197 gram per mole. So what we have to find? Number of atoms in 39.4 gram gold. So first of all, what is given? You see, molar mass of gold is given. How much that is? 197 gram per mole. That means what? 197 gram of gold contains how many number of atoms? 6.023 into 10 to the power 23 atoms. Now 1 gram of gold contains how many number of atoms? Then just we have to divide by 197, and that's why 6.023 into 10 to the power 23 by 197, that is the atoms contained in 1 gram of gold. Now how many gram gold we have? 39.4, and therefore in 39.4 gram of gold contains how much? This into 39.4. So that's why whatever this factor you got in 1 gram, just I'm multiplying with 39.4, and I'm getting answer that is 1.2 into 10 to the power 23 atoms. And therefore in 39.4 gram of gold, how many number of atoms are there? 1.2 into 10 to the power of 23. Okay. So next topic, assumptions of kinetic theory of gases. So on what basis or on what assumptions this kinetic theory of gases is built, we can say. So first one, it relates macroscopic properties, pressure, temperature, to the microscopic properties of gas molecules, that is speed, momentum, and kinetic energy. Means what? In this kinetic theory of gases, we will always relate pressure, temperature with speed, momentum, kinetic energy, etc. Okay, right? Speed, momentum, and kinetic energy always relates with pressure and temperature. How it is, that is what we are going to learn in this. So first assumption, every gas consists of extremely small particles known as molecules. So in every gas, you have very small particles, which we are calling it as a molecules. And size is negligible in comparison to the intermolecular distance, and that is 10 power minus 9. Next one, the molecules of a gas are identical, spherical, rigid, and perfectly elastic point masses. So what type of molecules are there? Identical means all are identical. They are spherical, rigid, and perfectly elastic. So if same gas is there, same molecules. If different gas is there, different molecules. It means oxygen, you have same molecules, but oxygen and nitrogen, you have different molecules. Okay. The volume of molecules is negligible in comparison with the volume of gas. So you see, complete volume of the gas and volume of one molecule is definitely negligible. One volume or volume of molecule is how much? 0.014% of volume of gas. This is what the assumptions, 3 assumptions. Next assumptions we will see ahead. Just note down. So let's see fourth assumption. Density of gas is constant at all points of the container. Means mass per unit volume is same everywhere. It is not somewhere more and somewhere less. It is uniform everywhere. Next one. Molecules obey Newton's laws of motion and their motion is isotropic. Isotropic means what? Same in every direction. Okay, it is not going to change with direction. Next one, see, this is time between collision and this is time between two successive collision. So this t is always negligible compared to t dash. So time during collision is always negligible compared to time between two successive collisions. And number of collisions per unit volume in a gas remains constant. Whatever the number of collisions are there, they are always constant. Okay, let's move ahead. Next assumption, no attractive or repulsive forces acts between the gas molecules. There is no any attractive force as well as no repulsive force between two gas molecules. Molecules constantly collide with the walls of the container due to which their momentum changes. Gas molecule will go and collide on the walls and due to that collision, their momentum continuously changes. Due to this, pressure is exerted by gas molecules on the walls of the container. Due to what? Change in momentum, pressure is getting exerted. Let's derive an expression for pressure of an ideal gas. Let us suppose we have n molecules and we have taken one cubical container whose length is L. How many number of molecules we have? Capital N. And we have placed them in the container which is cubical. So see here, I have taken this cubical container, you can see, and this is Y, this one is X, and this one is Z. You can see this length is L. Now this A1 and A2 is the area, and you can see this one molecule is going with velocity Vx, is going and colliding with this wall, and again it is moving in opposite direction with same velocity. So this molecule is having velocity Vx along X, Vz along Z, and Vy along Y. So if I want V bar, Vx I cap plus Vy j cap plus Vz k cap, and I want magnitude, its magnitude will become Vx square plus Vy square plus Vz square. What we did, we have placed some molecules in a cubical container, and these molecules are going and hitting this wall and coming back with another velocity, or we can say same velocity with opposite direction, and this is what its velocity is. And now we have to derive expression for pressure. So let's move ahead. Note down first this. Now see, due to the random motion of molecules, Vx is equal to Vy, V is equal to Vz, and that's why V square is equal to 3Vx square plus 3Vy square plus 3 Vy square is equal to 3Vz square equal to, okay. And now I want to find change in momentum. Minus mvx is equal to minus 2mvx. Okay. This is what change in momentum. Pf minus pi. This is what Pf minus pi. Pf is minus mvx. Pi is mvx. So delta P, change in momentum, is minus 2mvx. So this is what change in momentum when molecules collide elastically. Now let's find out time. So time is what distance traveled by molecules between two successive collisions to the velocity of molecule So distance is how much? While going, you can see back. While going, it is L. Yes, no, in the diagram you see, this is L. And again, while coming back, L. L plus L, 2L. That's why here 2L, and velocity is what? Vx. That is what? Time period. Or change, what you can say, time, just. Time between two collisions, we can say. Or distance traveled, or time taken to distance traveled, how much? 2L. Now frequency is reciprocal of time. So nu is equal to 1 by delta t, and it just I'm taking reciprocal of that, Vx by 2L. Now force exerted by single molecule, F is equal to, from Newton's second law, F is equal to delta P by delta T. So delta P already we have, how much it is? 2 mvx, and delta T just we have found. So just 2 mvx by 2L by Vx, 2 will get cancelled, mvx square by L. This is what? Force. Now this force, I am just taking ml outside, m by L outside, summation of Vx whole square. So small m into n by L for n molecules, Vx1 square plus Vx2 square plus Vx3 square plus so on. And now Fx is equal to mn by L Vx bar square, where v bar Vx bar whole square is mean square of x component of velocity. This is what force we have found it till now. What we did? Very simple. First we have found change in momentum, and then we have found time, and then we have used Newton's second law, that is delta P by delta T, and we got this, right? Note down. Now let's find out pressure. So pressure is defined as what? Force by area. P is equal to force by area. Now if I want along x-axis, then Fx by A. So Fx already we know, mn by L into Vx bar whole square divided by A, that is what? Pressure. For any molecules, V bar square is equal to Vx bar square plus Vy bar square plus Vz bar square, and that's why Vx bar square is equal to Vy bar square is equal to Vz bar square is equal to V bar square by 3. Okay, and just we are going to substitute this value at the place of this Vx bar whole square. What is that? V bar square by 3. Okay, and this area into length I'm going to replace with volume. You can see here this formula only I'm going to use. See here, this one you see, and here I have substituted mn as it is. This area into length I have substituted with V, and this Vx bar whole square I have substituted by V bar square by 3. Now this is equal to 1 by 3 mn by V, and this V bar square is nothing but Vrms. Okay, so what you will get? Vrms square is equal to V bar square, and that's why P is equal to 1 by 3 mn by V into Vrms whole square. This is what? Pressure. Okay, now pressure P is diagonal proportional to mn T by V, because Vrms square is diagonal proportional to T, and that's why at the place of Vrms I'm going to substitute T. This mn by V is as it is, just we have to keep T. This 1 by 3 is constant, and that's why P is diagonal proportional to mn T by V, where V is volume, T is temperature, n is number of molecules, and m is mass of gas. So see what we did, we have found the expression for pressure in this expression, means in this slide. Yes, no? Note down. So let's move ahead. Now next one, various types of speeds of gas molecules. Various types of speeds of gas molecules. First one, that is root mean square speed, and it is defined as the square root of mean of squares of the speed of different molecules. See here, Vrms is equal to under root of V1 square plus V2 square plus V3 square so on by n, and it is equal to under root V bar whole square. And this is what we have used in previous slide also. You can see here in the expression where there was V bar square, we have used Vrms square. Yes. So this is what? Root mean square speed. Now see, we got this P is equal to 1 by 3 rho VRMS whole square. Yes, P is equal to 1 by 3 rho VRMS whole square. Now just I am transferring this 3 this side. 3P by rho is equal to VRMS square. See here, 3P by rho. VRMS is equal to what? This 3 went here and rho down under root. VRMS is equal to 3P by rho. Now this rho is there. No, rho is equal to what? M by V. So when I am substituting this rho as M by V, this V will go up and M remains here. 3PV by M. Next, this M is there and this is PV. So I can substitute that with PV by M. I can substitute as RT by capital M. You know this PV is equal to M by capital M into RT in ideal gas equation. That is what I am doing here. Okay. And again same. I am substituting again 3 kT by M. This is also, you know, the relation between K and R. Yes. Okay. Okay. Right. Next one, note point you see here down. VRMS is dial proportional to root T. From this you can say VRMS is dial proportional to molecular weight from this. And VRMS does not depend on pressure if temperature of gas is constant, because as pressure increases, density also increases. Okay. VRMS remains constant. Okay. So note down. So next one, most probable speed. What is the most probable speed? It is the speed which is possessed by maximum fraction of total number of molecules of a gas. So see here, for example, 1, 2, 2, 3, 3, 3, 4, 5, 6, 6 kilometer per second. These are the some velocities. And from this, you see most number of times, which one is repeated? That is 3. And that's why most probable speed is what? 3. The most probable speed V is Vmp is equal to 2p by rho under root, which is equal to under root 2 RT by capital M, which is equal to under root 2 KT by small m. Same relation between R, K and M and capital M. So no need to explain again. Next one, average speed. Average speed everyone knows. It is just arithmetic mean of the speeds of molecules in a gas at a given temperature. V average is equal to V1 plus V2 plus V3 plus so on by N, and this is just average. V average is equal to 8P by pi rho, which is equal to 8 RT by pi M, which is equal to 8 KT by pi M. This is what the formula where K is Boltzmann constant. Next one, that is Graham's law of diffusion. What is Graham's law of diffusion? When two gases at the same pressure and temperature are allowed to diffuse into each other, rate of diffusion of each gas is inverse proportional to square root of density of the gas. Means what? Rate of diffusion is inverse proportional to square root of density. You can see here rate of diffusion, if I am denoting with R, R is inverse proportional to under root rho. Okay, rate of diffusion is inverse proportional to density, square root of density. And that's why R1 by R2 is equal to under root rho 2 by rho 1. This is what Graham's law of diffusion. Let's see one note point. Now VRMS is equal to 3P by rho. Already we have seen. So if this 3 and P is constant, then I can say that VRMS is dial proportional to 1 by root rho or inverse proportional to root rho. And that's why VRMS 1 by VRMS 2 is equal to under root of rho 2 by rho 1. So R1 by R2, because already I have here rho 2 by rho 1, under root rho 2 by rho 1. So can I substitute here VRMS 1 by VRMS 2? Yes. And that's why rate of diffusion, R1 ratio of rate of diffusion, R1 by R2 is equal to VRMS 1 by VRMS 2. Okay, understood? Note down. So let's move ahead. This is next topic, that is Dalton's law of partial pressure. What is Dalton's law of partial pressure? The pressure exerted by a mixture of several gases equals the sum of the pressures exerted by each gas occupying the same volume. Means what? See here, this pressure P is equal to F1 by A1 plus F2 by A2 plus F3 by A3 plus so on all the pressures, and that's why the net pressure is equal to sum of all pressures exerted by each gas. That is what P is equal to P1 plus P2 plus P3 plus so on. Next one, relation between pressure and kinetic energy. Relation between pressure and kinetic energy. So let's move ahead. Pressure already we have seen 1 by 3 Mn by V into Vrms whole square, which is equal to 1 by 3. This Mn I have replaced with capital M, that is divided by V into Vrms square, and this M by V is nothing but density, and that's why 1 by 3 into rho into Vrms square. Let's call this as equation number 1. This is what? Pressure equation. Next, now mean kinetic energy per unit volume. This is not only half mv square, okay? This is mean kinetic energy per unit volume, means energy per unit volume. This is, that's why you are getting one extra factor here, that is V. So 1 by 2 m by v Vrms whole square, and this is nothing but half rho Vrms whole square. Now from equation 1 and 2, if we will multiply this equation with 3 and this equation with 2, then you will get the same thing, and that's why 3 into 1 by 3 rho Vrms square is equal to 1 by 2 rho Vrms square into 2. You will get same. This is nothing but what P, and this is nothing but what E. This 2 as it is. So 3P is equal to 2E, and therefore P is equal to 2 by 3 E. This is what relation between pressure and average kinetic energy per unit volume. Now see here, this P is equal to 2 by 3 capital E we was having before. Now I am replacing this capital E with Ek by V. Ek is just kinetic energy, and that's why PV is equal to 2 by 3 Ek. That is what? Total energy we can see. Okay, so this is what the relation between pressure and kinetic energy. Note down. This one you noted. First note down this, and then this. Okay, let's move ahead. Average translational kinetic energy per molecule of gas. So an ideal gas, the molecules are considered as point particles. In ideal gas, all molecules are considered as a point particles. For point particles, there is no internal excitation, no vibration, and no rotation. What are the point particles are there? There will be no excitation, there will be no vibration, and no rotation also. Point particles can have only translation motion and thus only translational energy. These particles can have translation motion, and that's why translational energy. For an ideal gas, the internal energy can only be translational kinetic energy, and due to that, they may have only translational kinetic energy. Note down. From microscopic consideration, that is from kinetic theory of gases, because this one you can see average translational kinetic energy per molecule of gas. That is what we have to find. Yes. So see, from microscopic consideration, we got P is equal to 1 by 3 Nm by V into Vrms square. Okay. Then after this, PV, this V I am transferring here. So PV is equal to 1 by 3 Nm into Vrms square. Call this equation number 1. Now from macroscopic consideration, that is from ideal gas equation, PV is equal to nRT. We know this is your second equation. Now from equation 1 and 2, what we are getting, see, this 1 by 3 Nm Vrms square is equal to nRT, and therefore half M Vrms square is equal to 3 by 2 N by N into RT. Just I am transferring this 3 this side and then multiplying with 1 by 2. Then you are getting 3 by 2 R by Na into T. Already you know this part. R by Na is equal to K. So from this, half M Vrms square is equal to 3 by 2 kBT. Yes, what I did, just R by Na we have replaced with K. Already I have shown here how you got this Na is equal to N by N and all. You can see once. Note point, you see, E is equal to half M Vrms square, which is equal to 3 by 2 RT, and energy in gram is equal to 3 by 2, just divide by M, so K by M into T, and energy in gram is directly proportional to T by M. So whatever problems if they are asking you, you can use this. Okay. Next topic, Maxwell's law, that is the distribution of molecular speeds. So see, the gas molecules can have all velocities between 0 to infinity, but this is wrong. Why? Because now we know the maximum velocity which is possible is should be less than the velocity of light, and that's why it is not possible. Second one, though due to collision, speed of the individual molecules are continuously changing, the fraction of molecules having their speeds within a certain range remains the same at any instant. Means fraction of molecules having their speeds within certain range is always constant. So see, this is the equation. Nv is equal to 4 pi n m by 2 pi kBT whole power 3 by 2 v square e power minus mv square by 2 kBT. So this Nv, that is dn by dv, is called Maxwell-Boltzmann speed distribution function. dn is number of molecules with speeds between v to v plus dv. M is mass of gas, kb Boltzmann constant, and n is total number of molecules. If you will get problem on this, you can use it. Okay. See here, this is dn by dv versus v to v plus dv graph, and on this they have given you these velocities. Okay. So here Vrms is always greater than V bar is always greater than V of most probable. Okay, so which one is more greater? That is Vrms. And this relation you can see. Vrms is root 3 kBT by M. So V bar is equal to 0.92 times Vrms, and Vmp is 0.82 Vrms. If in problem also they have given this V bar, and if you want to find Vrms, direct divide with 0.92, you will get this. Or if suppose most probable is given, just direct divide 0.82, you will get Vrms. No need to substitute any other values. So these 2 points you can keep it in mind. Okay. Right. So note down. Next one, what is mean free path? So mean free path means the path traveled by a molecule between two successive collisions. If we will take the example of two drunkmans, whatever the distance they have traveled before colliding on one another, that is what I think what mean free path. Same thing here also. Two molecules before colliding on each other, what is the distance they are traveling, that is what mean free path. And this mean free path is nothing but total distance traveled by gas molecule between successive collisions divided total number of collisions, and its formula is 1 by root 2 pi d square n, where d is diameter of molecule, n is number of molecules per unit volume. Collision frequency root 2 pi d square v bar n, or v bar by lambda, where v bar is average speed of molecule, and mean free time, that is reciprocal of frequency, we can say, just take the reciprocal of this, you will get root 2 pi d square v bar n. Okay, 1 by, that is also. Okay, note it. See some note points. Lambda is equal to 1 by root 2 pi d square n. So lambda is inverse proportional to d square, where d is molecular diameter. Lambda is diagonal proportional to T, that is absolute temperature. Lambda is diagonal proportional to 1 by P, that is pressure. Lambda is inverse proportional to density. And lambda is diagonal proportional to mass of each molecule. Where lambda is what? Mean free path. This they may ask you in problems, you can note down. So next topic is degree of freedom. What is degree of freedom? The total number of independent ways in which system can possess energy. The total number of independent ways in which system can possess energy. Independent motions can be rotational, translational, rotational, or vibrational, or any combination of these. So see, degree of freedom, translational, rotational, and vibrational. Now, first of all, monoatomic gas. Monoatomic gas can move in any direction in space, so it can have 3 independent motions, hence 3 degree of freedom. How many motions? 3 independent motions, that's why 3 degree of freedom. Means for monoatomic gas, there is 3 independent ways, or there are 3 independent ways in which system can possess energy. For example, helium and argon. You can see the diagram. See here, this is X, Y, and Z. So monoatomic gas can move in any one of these directions, and that's why can have energy in 3 ways, we can say. That's why 3 degrees of freedom. Okay, note down. Next one is diatomic gas. So this diatomic gas, 2 atoms join rigidly one another through a bond. How many atoms? 2 atoms. Monatomic 1 atom, here it is 2 atoms and joined through a bond. 2 rotational motion and 3 translational plus 2 rotationals, and that's why you have 5 degrees of freedom. For example, hydrogen, oxygen, and you can see the diagram. This is what diatomic molecule, and it will rotate like this. Okay, it has 2 rotational plus 3 translational, and that's why 5 degrees of freedom. Next one is triatomic gas, nonlinear. A nonlinear molecule can rotate about any of 3 coordinate axes, and hence it has 6 degrees of freedom. Okay, how many 6 degrees of freedom for triatomic gas? Note down. We have seen triatomic gas has 6 degrees of freedom, but if suppose temperature is high, then it will have 1 extra degree of freedom, that is vibrational, and hence total 7 degrees of freedom. For example, NH3CO2, and the diagram for triatomic molecule is something like this, you can see. Okay, next is law of equipartition of energy. Law of equipartition. Equipartition means what? Equally distributed or parted, we can say. So see what it says. For any system in thermal equilibrium, the total energy is equally distributed among the various degree of freedom. So what are the energies there that is getting total equally distributed along each degree of freedom, and each degree of freedom associated with energy half kT, where K is what? Boltzmann constant. Total energy associated with each molecule is equal to F by 2 kT, and for n number of molecules it is F by 2 nkt. For 1 mole, F by 2 RT. For n moles, F by 2 nRT. So whenever you want to find this energy, you can use this formula according to the cases asked. Okay, for 1 mole, F by 2 RT. For n mole, F by 2 nRT. For n molecules, F by 2 nkt. Molecules means K will come. Even here also molecule means K is Boltzmann constant is coming. Okay, so note down. So let's see some note points. Specific heat, that is molar specific heat at constant pressure, is equal to F by 2 plus 1 into R, where F is degrees of freedom. CV is equal to F by 2 R. So whatever the F you have, you can just substitute here, you will get the Cp and Cv values. For example, monatomic gas, you see Cp is equal to 5 by 2 R, Cv is equal to 3 by 2 R, because just degree of freedom is 3. If you will substitute here, you will get this. Gamma is equal to Cp by Cv, that is 5 by 3 is equal to 1.67. This is for monatomic gas. Next one for diatomic gas, degree of freedom is 5. So if you will substitute here 5, you will get Cp is equal to 7 by 2 R, Cv is equal to 5 by 2 R, and gamma is equal to 1.4. For triatomic gas, Cp is equal to 4 R, Cv is equal to 3 R, degree of freedom 6. Just substitute here, you will get this. And degree of freedom is 6. At high temperature, you have 7. Gamma is equal to 4 by 3. That is just Cp by Cv, and you will get 1.33. Next, now this E translational, E rotational, and E vibrational, how to find, or what actually this is. See here, E translation means half m Vx square plus half m Vy square plus half m Vz square. This is just kinetic energy due to the translational velocity, we can say, or translation motion. And rotational energy is just due to the rotations, that is half I omega square. So if you have 2, then I1 omega 1 square plus half I2 omega 2 square. Half is there, okay? Half I1 omega 1 square plus half I2 omega 2 square. If 3 you have, then you can add one more. Next, what about this vibrational energy level? Because when you have high temperature, you are getting one extra degree of freedom, that is due to this vibrational energy, and that is half m dy by dt whole square plus half ky square, where k is force constant of oscillator and y is vibrational coordinate. Okay, so like that you can find out whatever they will ask you. And this is what the end of the chapter, that is kinetic theory of gases. Let's stop here. Bye.